Hi everyone, I'm Tomogno Hazra. I'm a postdoc at Rutgers working with Piers Coleman, and today I want to describe a pairing mechanism for triplet superconductivity that arises quite naturally from Hund's and Kondo coupling. So, the motivation for this study comes from these two materials, one of which has already been introduced. In both of these, you get upper critical fields in excess of the Pauli limit, sometimes by an order of magnitude. You have multiple superconducting phases, and in fact, several very extraordinary experimental observations, of which I'll highlight two aspects. In the transport data, you see a resistivity upturn and peak, which is characteristic of Kondo hybridization. In the STM data, you see a Fano line shape in the DIV spectrum, which is characteristic of co-tunneling of electrons into local moments. Together, these suggest that Kondo physics is a central character in the low energy physics of these systems, yet in the existing proposals for the pairing symmetry, Kondo hybridization does not play a role in the low energy physics, including superconductivity, with one exception. So, our goal today is to explore how the Kondo physics affects the superconductivity, and I'll show you that local on site interactions, the Hund's coupling and the Kondo interaction, can by themselves lead to triplet superconductivity. The key idea is that if you have a Hund's coupled if you have two localized f electrons in an atom, Hund's coupling wants to align the spins into a s equals to 1 spin triplet. And in general, crystal fields will pick out one of these to be the ground state of the local moment. So, written in this way, it's easy to see that local moments form a reservoir of strongly bound pairs whose triplet correlations are driven by the largest energy scale in the system, atomic Hund's coupling. It results in a triplet valence bond between the electrons in these two orbitals. Now, with Kondo hybridization, the triplet pairing correlations bleed onto the electron cloud that screens the local moment. So you might expect that if you have a lattice of such Hund's coupled local moments, the electron pairs would delocalize and become coherent, and leading to superconductivity. So, in analogy with the vanilla RVB picture that Anderson advanced for the cuprates, here we have triplet superconductivity arising out of a new flavor of resonating valence bond states enabled by Hund's and Kondo interactions. Way back in 1985, Anderson had also identified an obstruction for such local triplet pairs, that under inversion about the local moment, on-site pairs are even parity, whereas we know that on the Fermi surface, triplet pairs have to have odd parity. And he had pointed out that it was possible to have triplet pairs on atoms away from inversion centers, so that the sublattice degree of freedom would acquire the triplet pairs to acquire odd parity form factors. Now, this structural motif that you have at least two F shell atoms per unit cell is actually present in several heavy fermion superconductors, including good old uranium beryllium 13 and UPT3. In all of these, the upper critical field exceeds the Pauli limit, suggesting that there is triplet superconductivity. So, to summarize the big picture, Hund's interactions leads to triplet pairs trapped inside local moments. Kondo hybridization allows them to delocalize. The sublattice degree of freedom allows them to pick up odd parity form factors, so that the Fermi surfaces become unstable to pairing in the triplet channel. So, to demonstrate this key idea, we consider a two-channel Kondo model with the conduction electron Hamiltonian describing hopping on a two-sublattice BCC lattice. The lattice is obviously inspired by uranium ditelluride and cerium rhodium arsenide. In addition, we have the singlet Kondo channel, the singlet Kondo interaction with the usual isotropic spin exchange arising from charge fluctuations into the F electron vacuum. And we have what we call the triplet Kondo coupling, which is an isotropic spin exchange of the conduction electron spin with the local moment. This is obtained by integrating out the charge fluctuations from, say, an F1 Kramers doublet and a Hund's coupled high spin F2 singlet. Now, the form factor of the triplet Kondo couplings are determined by the symmetry of the F2 ground state. I should stress here that this is not ferromagnetic Kondo coupling, which we know scales to weak coupling in the single impurity case. Rather, the XXZ anisotropy allows it to scale to strong coupling, just like the antiferromagnetic Kondo. Uh, anisotropic spin exchange has been used earlier in our group to advocate a triplet resonating valence bond pairing mechanism for the iron-based superconductors. Okay, so in this model, what we do is we represent the spins in terms of spin-on bilinears, and following standard part-on mean field construction introduced in these papers, we decouple this Kondo interaction into a singlet pairing and hybridization mean field. This does not give us superconductivity per se, even though there is a delta here, because in this representation there is a SU2 gauge symmetry that converts the F dagger to F, and therefore converts particle hybridization into delta into particle hole hybridization V. So going forward in this work, we fix the SU2 gauge of the spin-ons so that the particle hybridization in the singlet channel is 0. And we can similarly decouple the triplet Kondo interaction into a triplet pairing and a triplet hybridization mean field, and then solve the self-consistency equations in the space of these order parameters. Now, in the single impurity case, two channels tend to compete. So you would expect that one of these two channels would have finite order parameters. However, on the lattice, hybridization in one channel leaves a Fermi surface that is unstable to pairing in the other channel. So for these parameters shown here, what we find is as you cool the system below a certain temperature, below a certain Kondo temperature Tk, singlet hybridization sets in the singlet channel, and you have a large Fermi surface. And at a lower temperature, pairing sets in the triplet channel, and you have a superconducting gap on the Fermi surface with a line node wherever kappa z, the form factor, goes to 0. Now, in this phase, you could integrate out the spin-on degrees of freedom and just look at the conduction electrons. So this is the zero energy anomalous self energy of the conduction electrons, and it resembles a pair potential with the d vector pointing along z. So the pair spin is along the xy plane, and the upper critical fields in the z direction are expected to overshoot the Pauli limit significantly, as we do find in the materials of interest. Now, the form factor of the pair potential was determined by the form factor of the triplet Kondo coupling, which in turn was determined by the triplet by the symmetry of the F2 Hund's coupled ground state. In a real system, there are several Hund's coupled singlets available, and each of these leads to a triplet Kondo coupling with a different symmetry and opposing pairing tendencies. So magnetic fields, pressure, anything that couples to these F2 singlet states will change the relative strength of the Kondo hybridization in different channels. And so this pairing mechanism that we introduce is very flexible, and it's readily generalized to account qualitatively for the multitude of order superconducting phases observed in the experiments. So to summarize, Hund's coupling leads to preformed triplet pairs trapped inside local moments. This enables a triplet Kondo coupling, which imbues the conduction electrons with triplet pairing correlations. And this leads to a very natural pairing mechanism for triplet superconductivity in heavy fermion systems enabled by Hund and Kondo interactions. Thank you.